A warm welcome to the lecture on the subject of wavelets and multirate digital signal processing, in which we proceed further on the theme of the two-channel filter bank. You will recall that in the previous lecture, the 10th lecture, we had looked at what happens when a sequence crosses a downsampler and an upsampler. I would like to put before you the effect in the Z domain once again when we cross a downsampler and when we cross an upsampler. So, today's lecture, as I said, is entitled the two-channel filter bank. And we intend in this lecture to talk about this structure, which we have been repeating often again. But today we intend to analyze it threadbare, so to speak. Now, remember that H 0 was a low pass filter, H 1 a high pass filter. It is helpful to get this structure firmly embedded in our consciousness. It is a structure often used in the implementation of a discrete wavelet transform, for example, of the Haar multi-resolution analysis. So, it does no harm to repeat the structure more than once. We have been looking at this structure almost in every one of the last 2 to 3 lectures, but no harm done. Anyway, here is the structure once again. And what we intend to do finally today in this structure is to relate the Z transforms at every point in this structure. Let us start doing that, and to do that, let us first recall what happens when we go past a downsampler and an upsampler. So, as I said, let us look at the upsampler first, a recall from the previous lecture. Noted from the previous lecture that if you have x in n going to an upsampler by a factor of 2 to produce x out n here, then x out z in this case, maybe to be specific we could say x out u to denote upsampling here. So, x out u z is x in z squared in this case. Let us similarly see what happens when we go past a downsampler. So, for the downsampler by a factor of 2, remember we had analyzed in detail the case of a downsampling by factor of 2. We had indicated how to generalize, but it was a little more complicated. So, here we have x out d n, if you please. And in fact, we had noted that this operation of downsampling by 2 was equivalent to 2 operations. And let me spell out those operations once again, following which I shall write down the Z transform here. So, we had agreed that this operation of downsampling by 2 can be split into modulation with half 1 raised to the power of n plus minus 1 raised to the power of n first, followed by inverse upsampling by 2, inverse, We had noted that upsampling by 2 or upsampling by any integer factor for that matter was an invertible operation. And in fact, this is also evident in the Z domain. And therefore, we can talk about the inverse here. Now, based on this, we had written down the Z transform. So, we had said x out dz here is half x in z raised to the half plus x in minus z raised to the half. We had derived this towards the end of the previous lecture. And of course, if you did not wish to go beyond the inverse upsampler at this point, instead of z raised to the power half, you would simply have z. So much so then for the z domain effect of downsampling and upsampling. Now, what do we intend to do next? We intend to use these relationships to build up the relation between the Z transform of the output and the Z transform of the input. So, essentially we wish to establish the input output relationship in this 2 band or 2 channel filter bank in the Z domain. Now, of course, I must make a remark here before we embark upon this activity. We are assuming that the Z transforms exist at all points. There are rare situations, or maybe not so rare, where that may not be true. But for the moment, we shall ignore those situations. They are not very frequent in practical applications, and therefore, we can comfortably begin with the assumption that the Z transforms exist at all points. Of course, I do not mean the Fourier transforms exist, they may or may not. Anyway, coming back then to that 2 channel filter bank that we began with earlier on in this lecture, I put it back before you here. I intend now to relate y z and x z in this diagram. And towards that objective, let us number the Z transforms at different points. In fact, let us give the sequences names. So, let us call this y 1, let us call this y 2 and so on. And the very output we shall just call y without any subscript. So, accordingly this becomes y 3, this y 4, this y 5, y 6, y 7, y 8 and then of course, y 9 is simply y. So, with this then, let me write down the expressions for each of these. So, let us begin with y 1. Y 1 is easy and so is y 2. In fact, if we look at the Z domain relationships, y 1 z is simply x z times h 0 z. And similarly, y 2 z is simply x z times h 1 z. When we filter with a filter of system function h 0 z, the effect is to multiply the Z transform of the input by the system function of the filter to produce the Z transform of the output. And therefore, y1z and y2z are easy. y1z is h0z xz, y2z is h1z xz. Now, we have before us the relationship that emerges between y3 and y1, and similarly between y4 and y2. As I said, downsampling by 2 is equivalent to a modulation and then an inverse upsampling by 2. So, it is easy then to jump from y1 to y5 first and y2 to y6, because if you think of this downsampling by 2 operation as a modulation followed by an inverse upsample by 2, the inverse upsample by 2 cancels with this upsample by 2, leaving only the modulation here. So, this is a strategy which we might find useful in some circumstances in analyzing multi-rate systems, particularly when you have a downsampler followed by an upsampler. If you have a downsampler followed by an upsampler of the same factor, it is sometimes easier to go past both of them and then jump back behind the upsampler. We will do exactly that here. So, we will put the relation between y1 and y5, and y1 to y5 is essentially just a modulation. Modulation by 1 raised to the power of n plus minus 1 raised to the power of n multiplied by half. And therefore, the Z transforms are easily related. y5 of z is half y1 z plus y1 minus z. And there is a very similar relationship between y2 and y6. Put this back, y2 and y6 are related by the same modulation. Let us write that down too. So, we have y2 is modulated to obtain y6, and therefore, y6z is half y2z plus y2 minus z. In fact, this jumping across the downsampler and the upsampler was useful because it brought us quickly towards the output. Now, we are only almost one step away from the output. That step is also not very difficult to take. We just have two filters followed by a summer, which is easy to do in the Z domain. So, let us complete that exercise. So, now we are here. We know what y5z is, we know what y6z is. y5z is acted upon by a filter with system function G0, and therefore, the Z transform at the output here after G0 is the Z transform of y5 multiplied by G0. Similarly, the Z transform at the output of G1 is y6z multiplied by G1z. And in fact, let me take you one step even further. After all, yz is obtained by adding y7z and y8z, and therefore, we already have yz before us. Let me write down those steps quickly before you now. So, we have y 7 z is y 5 z times g 0 z, and y 8 z is y 6 z times g 1 z, whereupon y z, which is y 7 z plus y 8 z becomes, let me put before you the expression for y 5 and y 6 once again. So, let us take y 6 as an example. Now, you are going to involve y 2 z and y 2 minus z. Y 2 z, if you recall, is x z times h 1 z as an example. Now, when you take y 2 of minus z, you would get x of minus z multiplied by h 1 minus z. So, in fact, let me put that down. What I am trying to do is to identify a form of the expression. So, this y 2 of minus z has two terms embedded in it. So, let us focus, let us say for example, on this term here, y 8. So, y 8 z, as I said, is going to be y 6 z times g 1 z. Y 6 z is going to be related to y 2 z, and then y 2 z is further going to be x z times h 1 z, whereupon y 2 minus z is going to be x of minus z times h 1 minus z. What I am trying to bring out from this argument or these equations is that each of these terms is going to have a contribution from x of z and a contribution from x of minus z. Now, later on we shall interpret these terms x of z and x of minus z, but for the time being all that we need to do is to identify that there is an x of z set of terms and x of minus z set of terms, which we can together write down as follows. So, we will say y z in total is of the following form. It is going to have some system function multiplying x of z and some other system function multiplying x of minus z. And using all the equations written so far, we can write down these two system functions, call them tau 0 z and tau 1 z. Indeed, tau 0 z has the following form. It just requires a little bit of algebra to get here. So, I would not actually do all the steps, I am sure all of you can do them. And now, we write tau 1 z as well. So, tau 1 z would be g 0 z h 0 minus z plus g 1 z h 1 minus z. Now, it should be noted that in tau 1 z, which is what multiplies x of minus z, you involve h 0 of minus z and h 1 of minus z. So, you never involve g 0 minus z or g 1 minus z. The z replacement by minus z is only for the analysis side. Anyway, with this little observation, we now write down y z once again for clarity. So, y z is a linear combination in the z domain, of x z and x of minus z. What does this mean? What do you mean linearly combining x z and x of minus z? You see, if the x of minus z term were not to be there, then we have a simple expression there. Y z is some function in z multiplied by x z. That is the good old linear shift invariant system for you with a system function, and in this case, if tau 1 z were to be absent, the system function would be simply tau 0 z. Tau 1 z is the troublemaker here, and we need to understand first what this x of minus z is. What does it do spectrally? What does it do in the time domain? So, let us understand that.